Okay, so next session is by Daniel and Harold. So Daniel, we already know, is the most contributor of Noj and parent of this whole community. And Harold is the person who is the most active. I see helping out, besides Daniel, obviously, and has I was just checking GitHub and has done more than 40,000 edits in TMD. So, so welcome. Yeah, over to you guys.
Thank you.
Yeah, thank you, Kiran, and I'm so glad that you're here because you are the one to slow us down and tell us where we're not making sense, and yeah, and that's the point. So on this session, we are hoping to be stopping and getting confused and wondering about, and that's the way it is going to be, hopefully. And we'll just dive into a REPL session and practice a few things. And yeah, maybe I'll share the screen for a moment, and Harold will be guiding me. Is it okay to ask Harold that you will say something about yourself for the beginning?
Yeah, that would be, yeah, that's great. Thank you. Yeah, I'm here. Daniel is the friendliest person in this entire community. And when he asks in a nice way for you to come, you just say yes. It's a total honor to be here. It's so cool to see this kind of stuff being organized. I'll say a few words about my background. My training originally is in mathematics. I did combinatorics and algebras and very abstract things like that. But I've made money doing software the whole way. So I have over 20 years of doing software startups. The first software startup that I worked at was split into a couple of different pieces, and one of the pieces was sold to NVIDIA. And so I worked at NVIDIA from 2008 to 2011, which was a really interesting moment in their history, maybe less interesting than this moment, but pretty interesting. And since then, we've been doing everything in Clojure after that. So the two startups after that, we've done everything in Clojure. The most recent one is called tech.ml.dataset. That's the first one where I'm a part owner. And we're committed to doing everything in Clojure, and we just do consulting for other businesses, doing work on contract basis. And I try to steer it towards some mathematical things that we know about, but everything is also web development. Obviously, it's the 21st century. So, and we're very convinced that Clojure is the best tool for doing the kind of work that we're hoping to do. I think what to say here about just a short history of the involvement of some of these open source projects. It was around 10 years ago at the previous startup. We hired a very, very, very smart engineer, and they came in and said, oh, we're doing things with predictive modeling and data sets and things like that. In Python, there's this thing called pandas, and this is how we organize all of this data. And it was like, oh yeah, what's that? And so learned about that about 10 years ago. And the history of TMD and the rest of the things we're going to talk about today sort of stem from that moment. It's like, oh, well, we're committed to doing this kind of modeling and data science in a functional way. And we believe Clojure is the best language for functional data science. And if there's a powerful tool out there, we're going to need it. And so it's, yeah, the whole history of all this open source is the development of basically that. And the most visible piece of that is TMD, which is in a lot of ways a sort of highly functional pandas.
What is TMD? What does it stand for?
Oh yeah, TMD, okay, is tech.ml.dataset, which is an open source library that is maybe our most popular open source library for organizing data in a sort of tabular way, in a way that someone coming from R or pandas might be familiar with, though also in a very different way because it's functional. Yeah, that's we'll say that there. Oh, it's on the screen now. Yeah. And that's a library that we've invested a lot in, and it's the core of the work that we do day to day in our business. And it's also used widely by other people in this community to do their work as well. And so that's what we're talking about today. And in particular today, we're going to talk about, I believe, the pieces that it's built out of. So when we go deep dive, there are libraries underneath TMD that sort of enable all the characteristics, the performance, and the functionality of it that we like. So that's what we'll talk about today.
Fantastic. Thank you so much. Maybe briefly about myself. My background is math and statistics and probability theory and community building. And that's what I do nowadays at the SciNoj Group, at least for now, while I have some time. And I'm so glad to have this session now. And maybe one thing we can hope to have in the discussion part at the end maybe is a little more about your experience consulting. And I think you, Harold, and you, Kiran, maybe you have some things in common, the kind of companies you've created are in a way similar and different, right? So maybe that's a nice discussion to have later on, I believe. And so maybe I will share the screen for a moment, or maybe for a long moment, and we'll just dive in, if that's okay. And
great.
Yeah, so I think you see my screen now. I'll just move a few things around and, maybe like that. This here, this, that. So, right, and so we just have a namespace with a series of examples, mostly by Harold, that will kind of let us learn a bit about a few of the libraries we care about. But maybe before that, let us just look into the broader names like landscape. So here's like a code example. Maybe I'll narrow down to this. So this code example, somebody is writing. Thanks, Siavash. And by the way, maybe I'll just mention that we also have the Zulik chat here. But I guess we have both. So I'll just kind of mention the Zulik chat again. So here we have the SciNoj Light channel, and here we can search for the deep dive, and we can also write here and follow up later on. This way things will not be lost. And great. So here we are. So just a little code example, that just a little taste of a few things mixed together. Here we have, for example, this function from fast math random that we did meet earlier today. And we have dtype-next for, creating these array-like constructs, which we're just mixing a few things. And the story of what we're creating here is that, it is, maybe I'll share the screen here. We're creating a little data set, right? Where we have x running integer and y, some number that depends on x in a certain way, but also evolves randomly as an evolving sum of some things, like a random walk of normal random numbers added together. And we don't make sense of it so much, but we create a table of that, and then we can visualize it as the random walk. And then we can also add a smoothing line to kind of make sense of it better. And this is just a little example of the little parts of the whole story we're trying to create, which is the SciNoj toolkit, which is all built on top of the stack that Harold talked about. And so we have tablecloth, for example, which is just a wrapper around tech.ml.dataset that was mentioned by Harold. And we have tablecloth for plotting and fast math for random numbers in this case, and metamorph.ml for this idea of a design matrix that allows us to kind of express a formula for the smoothing line. So maybe we'll dive into a few of these, but the idea is to begin deep down at the deepest roots as we can, and maybe not go much up. So the hope is that everybody here will be slowing us down, and we will stay down at the roots as much as we like, and maybe go a little bit up. So that's the plan. Maybe I'll share another thing that we had
Yeah, do we
yesterday.
have the diagram of the,
Oh, yeah. Right. So I think maybe it is bigger now. I believe you can see that. So that's a discussion we had yesterday in the Zulip chat, and our friend Join R, who is also very much involved in the whole journey of thinking and helping people with this whole stack. Join R created this nice diagram that kind of tries to draw the landscape of a few components here. And you see that deep down at the roots, we have something called ham-fisted that we haven't talked about yet. And above that, we have something called dtype-next that we did talk about slightly this morning, this array programming library. Maybe we'll spend a lot of time with ham-fisted and dtype-next. And of course, above that, we have the tech.ml.dataset that Harold mentioned, which is the, table processing library. And on top of that, the layer of table cloth and metamorph.ml for machine learning, and table plot for plotting, and fast math nearby, and so on. So that's one way to look into the landscape. And maybe, Harold, you wish to comment about that before I move further? Any thought about this diagram by the joiner?
Yeah, I really like this picture of it. It captures the kind of layer cake of it. The work that we do day to day is often with TMD, tech.ml.dataset, which is sort of in the middle here. Equivalently, tablecloth. I think tablecloth is strongly preferred by people who have experience with other table systems. I think it provides a lot of the functionality of TMD in a way that makes a lot of sense to people coming from different backgrounds than we happen to have, which is extremely valuable. I think what's below TMD in this picture, Tech.io and Chart showed up in here as well. But the dtype-next in particular, as the story of TMD, and again, like 10 years ago, finding out pandas exist. At that time, we were already doing everything in Clojure, and we had organized a lot of data into big vectors of Clojure maps. And this was actually working pretty well for us. And we had escape hatches when that was insufficiently performant or data got too big. We put things in Postgres and did extra work when necessary. But the big insight of pandas and NumPy and how that connects to TMD is this idea of like the column-oriented structure. A vector of maps is perfect, especially if that works for the problem at hand. But there's trade-offs and lots of potential upside to transposing this understanding from a vector of maps into a more column-oriented arrangement. The first one that I always like to think of here is with a vector of maps, you store the keys with each map. When you transpose it into a column-oriented understanding, you store the key at the top of the column once, and then you can store the data down from there without copying the key on each row. This is kind of just like the first insight into why a column orientation may be good. There's obviously many other benefits. But as soon as you've done that, it's like, wow, how are we going to store this column of data? And how are we going to capture this potential benefit of, packing the data into a column rather than understanding it as a sequence of maps? And dtype-next is on this picture. There was something that came before it that was just called dtype. And the first idea there of storing that column is like, well, I know what's tight in memory. It's a Java array. And dtype was just a really nice layer on top of Java arrays that allowed us to use them with all the data types that we needed to very conveniently, and to also understand the, in a sort of closure-y way. There were, we ran that to its logical conclusion, and it was great. And about halfway in this 10-year history, or maybe more like 6-7 years ago, it was painful working with all of these Java arrays. And we are Clojure programmers, and we love the Clojure data structures. Like love them. And the idea for dtype-next, which was like, what was going to come after dtype, was we want all the benefits that we got from packing the data, but we want to be able to, we want it to be closer to the Clojure data structures that we know and love. And that was the invention of ham-fisted at the very bottom here. So this is kind of a funny pun. There's the papers that Rich originally read and developed the data structures from have some acronyms in them with H's and M's and F's and A's and these sorts of, there's these array-backed hash map trees and these sorts of data structures. And the implementation of them that's inside of Clojure isn't suitable for this kind of tight-packed representation of data. And when we wanted that, and in particular when Chris wanted that, Chris is my business partner at tech.ml.dataset, who's done the lion's share of the development of all the great things that we use. He reread these papers and sort of projected them through this lens of wanting to pack data into columns. And he did it in a very ham-fisted way. he re-implemented all of that stuff in a way that's much more sensitive to the JVM and the underlying machines, and to this idea of columns of packed data, but with all of the insights that we could carry forward from the Clojure data structures. And so I think we'll see this in the code examples, but that's a short historical perspective on that picture and why things are split out the way that they are. Thanks for driving the picture, Daniel. Doing a great job.
Oh, thank you. Yeah, that is great. Yeah, so thank you for this background. Yeah, and maybe, I'll mention one place where people can search for these links, and that is the SciNoj book, the SciNoj toolkit, which is wrapping a few of these libraries by the Tech Ascent group, as well as other libraries. And here in the list of underlying libraries of SciNoj, you can see a few of these high performance computing libraries and the additional layers on top. And yeah, maybe we'll begin with these today. And maybe I'll share a little code example to kind of make sense of something that you showed us, if it makes sense, before we dive deep down.
Great.
So let us create a data set, right? So I'll be creating a data set with tablecloth, which is the, as Howard said, that's maybe the kind of more familiar layer on top of tech.ml.dataset. And so, for example, we can create something like, maybe let's have a range of number, or maybe a few random numbers, and let us turn that into a data set. Right, so, yeah, maybe we'll do it like that. And right, so we have this data set, and this data set, we can add columns. Maybe let's add, let's call it I. It will just be a range of numbers, right? So now we have also this running number and so on, right? So what is that? So this is a data structure, and let us call it maybe a data set. So the type of it is a data set type defined in the tech.ml dataset library. And as Harold said, that is a map where the keys are the column names and the values are whole columns. It is a column data structure, right? I'm just kind of trying to repeat what you said. So if they ask, is it a map? It is a map. What the keys are the column names, and the values, let us print them below. The values are two columns, the X column and the I column, right? And they are printed in this fancy way where columns are printed, right? And now you see, we only had to mention the column name once. In a way, we didn't need to actually create those many maps that would take so much space and expression, but it could feel like we also have our rows as maps, right? So we could take our data set and look for the rows of this data set. And we can ask to view them as maps. And then when we look into that, it feels like a sequence of maps, a vector of maps. And it is a vector of maps. If we, look into one of these, like the first one, and ask, is it a map? It is a map, but it is not the usual closure persistent map that is sometimes heavy in memory and has lots of overhead, storing the keys and the values. No, it is another type of thing. Another type of thing, which is a special type defined, I believe, in tech.ml dataset or in one of the other libraries. And it is just a view towards the existing data structure in memory, which is still a column data structure. And that is kind of mind-blowing that we have a column data structure, which is efficient. If we have number types, it will just be these condensed arrays of numbers. But it feels like a vector of maps, which is the joy of closure that many closure people like. So that's a little taste of it on the higher level. And that's kind of related to something that Harold said. But now in a moment, we'll dive into the lower level. Yeah, maybe maybe you're going to say something before.
Yeah. I really like this demonstration right here. And that type that's revealed there, we're headed down towards the roots. This type, and I really like Daniel. It does feel magical, because if you captured that object, the first of TC rows, and you associate something onto it, it's a map. You add a new key to it. It really, really, really feels like a closure map. The Z is now 99 inside this map. And you could start to think about what's the equivalent thing you might do in pandas. But we'll set that aside for right now. Importantly, this is capital F functional and immutable. So nothing about DS changed here at any of these steps. And the value that's finally returned at the bottom of this, it might be interesting to wonder what the type of that is, but it also is sufficiently closure map-like that you can just go back to work. Yeah, and it has all of the properties that we really have come to, that we've built everything on here, which is the persistent immutability. And that's thank you.
Yeah, thank you so much. Yeah, and by the way, earlier today, in the beginning of, many hours ago, somebody asked about, about mutability, right? So yes, this is, as you said, that's all functional, and still, the underlying data structure in memory could be mutable, because dtype-next does have these mutable versions of array-like structures. And if we are holding those views over that, then it could actually be fun to think about mutating them and wondering what might happen to the views. Maybe at some point we could try that. That could be interesting. But yeah, maybe that's not the first thing to try.
We can
Yeah,
reinvent some of the Python foot guns.
Right. Yeah. Yeah. And maybe just for the sake of completeness, we could also ask for the rows not as maps, as vectors, right? And then it looks like that. Sorry, just vectors of numbers. Yeah. And then we ask for the first one. We ask, is it a vector? Oh, sorry. Maybe let's keep it like that. And then let us ask for the first one. Is like that. Is it a vector? Yes, it is a vector. What type is it, right? Is it the usual closure vector? No, of course, it is another thing, something defined in ham-fisted in the lowest level of this story, right? And so on, right? And yeah, it is tempting to check, right? Can we conj a number to the first? Yes, we can, right? And then, so it is all kind of the same thing, right? And what type is that? Still that low-level thing in ham-fisted. Yeah, lovely. So that is that. And maybe before we dive in further, maybe I'll share another image. And just because the point of this diagram by Joyner is, it is a map of the landscape, but it is also an example of the great conversation we're having at the Zulip chat. And I wish to kind of use this opportunity to encourage people to join the Zulip conversation. And some people, like the helpful joiner, you will meet only there. And like Harold, every day it's helping everybody. So yeah, and another thing that happened was this diagram by Timothy, which is another flavor of that. And that's actually created by Hami, which is a closure-based diagramming tool, which is so amazing and so aesthetic. And I'm playing with it these days. And one of the fruits of this process, which is kind of a byproduct of this discussion, is that we'll start creating maps of the landscape in different ways. And there are some fascinating conversations with Timothy these days about the way we can create a picture of the landscape that will allow people to find their way to the different parts of the story. So that's another promising direction on the highest level of things. But now we go deep. Is that right? Yeah. So maybe we will kind of go through this series of examples by Harold, unless there is any other thing you were going to say before we do that.
No, this sounds good. Okay, so now we are going to the absolute bottom. I like how Daniel has organized this, because now we have some context. What are we doing? We have tables of data at the top, but at the bottom there's many interesting pieces here, and they're pretty well factored. We use ham-fisted outside of TMD also every day. We have a branch of our business which is just making other people's closure programs faster. Our clients always want their answers sooner. And sometimes that doesn't mean using Clojure and getting them in a week instead of a month. It means we uploaded the JSON file 100 milliseconds ago. Where are the summaries? And so when it comes down to that kind of getting the answers faster, we are very often replacing some Clojure, double arrows with ham-f stuff. And it can just go faster, and it has enough in common with Clojure that it can, in some sense, just be dropped in. And so that's this first example here.
Sorry, I have to stop you, Harold.
Okay.
I'm just browsing the API docs of ham-fisted, and I did run into this list of bars of functions. That's kind of funny. What is that? So I couldn't not ask what that is.
So here's the thing. The JVM is amazing. The JVM I think when you think back of the history of Oracle and earlier Sun and the Java language and how all of this and set-top boxes and 5 billion devices and blah, 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 the JVM is amazing technology. The Java language is like big question marks all over the place. Why did we let the interns like make a standard library questions? But the JVM is amazing. But it was specified very early. I'm decreasingly young, but I was very young when it was specified. And yeah, and they made some choices about primitive data types that can't like that everyone is just rolling forward with. So when we made dtype, the very first dtype, one of the examples that I think we'll get to later is when you open an image, one view of the image that you really want is each pixel as 3 bytes, R, G, and B, and you want those to be unsigned numbers in the range of 0 up to 255. And this representation of numbers is not convenient in the JVM. It's possible, everything is possible, but it's not convenient. And so when you find those, the very first version of dtype, one of the reasons we had to abandon it is it took a very, very, very long time to compile. And it took a very long time to compile because this was like start your REPL. It took a very long time to compile because there was a sort of combinatorial set of macros that would sort of handle these. It made it very convenient to work with some of these data types that the JVM doesn't make very convenient to work with. And those macros generated lots of code, and the Clojure compiler turned that lots of code into lots of classes, and things were, yeah, the startup times were absurd. But yeah, you're seeing some kind of you're seeing our now best ideas about how to do that in a way that that makes a nice compromise. So we can still start the REPL up quickly, but we can still have good ergonomics when working with different containers of these different types. And one of the deep insights here is that, yeah, longs and ints and doubles and floats are basically enough. And then from there, you have to do some clever things to get the like shorter types, 8 and 16-bit types. But yeah, dtype-next, when compared with dtype, is dramatically simplified, despite the fact that that image that's still part of the.
Yeah. Sorry, I had to ask, but now you can go
that's
there.
pretty good. That's pretty good. I haven't seen it blown out in exactly that way, but that's good. All right, back to this example. Okay, the construction noise is going. Is it bothersome to people or?
No.
Okay, great. All right, so let's go. We could go sort of line by line here. The top half here is Clojure. Range. What do we got? 10 million. Okay, so this is a list of numbers from O up to 10 million minus 1. And then we're shuffling that. And then we're putting it into blocks. Partition all 10,000. We'll take each 10,000 of the shuffled numbers and put them into a separate sequence. Then map. For each of those sequences, sort them. So you're going to get the range of 10 million split into smaller sequences, each sorted. And then we're going to do nothing with that. We're going to call count. Count in Clojure is kind of the quintessential way to make sure it's realized. This whole structure here is very lazy. This is one of the things we love about Clojure. It's a bunch of nested, lazy sequences. It's not using very much RAM, and it's not using very much time until you count it. That will force the realization of all of those sequences. And this was coming up, this came up in a real world context where we had a very large number. 10,000 is reasonable here, different sequences that were all being merged together, that were sorted. And they, the algorithm in question was spending a lot of time managing the sort of merging of these tens of thousands of sorted lists. And this just popped out as a great example of Hamath, because in the bottom half here, we have, if you squint, it's very similar. You've got a range of 10 million things. You've got the capacity for shuffling them. You've got the capacity for partitioning them. Map and sort are still on the screen, and count. And the bottom one is faster. It's taking, on Daniel's computer, 5% of the time. Is that right? Am I reading it right? Yeah. So yeah, this is a speed up of 20x by typing Hamath a couple times and LZNC a couple times. And maybe you could try to do that without even knowing what's going on and just get on with your life. How much do we want to talk about? What's interesting about this to you, Danielle, is my question.
Yeah, maybe we'll just say that we have 22 minutes till the end of the talk part, and then we have 20 more minutes of discussion.
Great.
Right? And yeah, so maybe could you explain what lazy and non-caching means?
Yes.
We didn't mention it many hours ago today, but you'll explain it better.
Okay, I'll explain it again at least. So the idea here, the closure lazy sequences that we all know and love, it's documented, and it's documented great and very clearly, but they have a design choice built into them, which is that they cache their results, which means that once you've realized a lazy sequence, the values inside of it are in memory, and this is quite good, especially if you have to go back to them and they were expensive to compute. So there's great reasons for caching. Excuse me. There isn't like a switch though where I can say, "Hey, Rich, give me a lazy sequence that doesn't cache." Later, there are transducers that we can drop into Java, and we can get iterators, and there's streams, and there's other things. But your Clojure lazy sequences are caching, and you don't get to choose. And that choice has trade-offs, and most choices do. So the main one is, and the one that people hit first typically, is they will realize some large sequence and run out of memory because they didn't realize that that the sequence was, had cached all of the values, and the sequences are potentially infinite, as we know, and so you run out of RAM. And so the very first question that sort of drives this development is, what's it look like? We like that it's lazy, but what's it look like if it doesn't cache? And there's a whole namespace here, ham-fisted lazy non-caching, which is just an answer to that question. We've got our lazy sequences. They feel like Clojure lazy sequences, but we know that they're never going to cache. And this, of course, puts us in another realm of the trade-off space, where, in particular, you're probably not going to have that problem where you accidentally held onto the head of some sequence that cached a lot of things and run out of RAM. Hooray, that's very good. You're probably going to have different problems, like part of the realization of that sequence wasn't pure, and it generated a random number, or it got something from the internet, or it did any number of things, looked at the computer's clock. And then you're going to have a different kind of surprise where it's like, whoa, I went over my sequence again, and it did the work of going back to the internet. It generated a different random number, and time is later now, and it branched into something that launched the missiles instead of sending the flowers or whatever. if you go over the sequence again, there may be surprises. And this is quite good. It's very important to the improved performance here. The part of what is slow about the closure one is it's holding on to more stuff than it needs to. Thanks.
Yeah, maybe. Yeah, I think that I believe it clarifies a little bit. So maybe we'll have a little taste of the other things, the other examples you prepare. That's really great. Yeah, and
Great.
maybe at some point, Harold, I'll ask you about the relationship between ham-fisted and dtype-next, and in a moment we'll see dtype-next, right?
Yeah, great. Yeah, perfect.
Yeah. So maybe here there is a little example that maybe we'll not spend so much time with that
Great.
Just those set and map structures that you have in ham-fisted. Would you like to say something about them?
Yeah. They went. Yeah, if you want to find out what a more high performance closure could be that verges more towards mutability but still presents an immutable interface, you want all the data types. So we have all of the closure data types and many of the Java data types, and we've implemented them in a way where they interoperate perhaps a little better than the original closure stuff. I mean, we had the huge advantage of seeing all of Rich's work. I think what I want to say about this example is there's a temptation when you're trying to make a closure program faster to drop into Java and just, I'm going to write this bit in Java and I'm going to get the answer faster because I'm not going to be doing, all the extra work that closure does. But there you run into pretty quickly, closure has some very friendly things, like the notion of equivalence in closure is very, very powerful. And so this is just, a slightly funny example here where if you drop down and you make a Java util hash set, and then you add the integer one and the long one into it, then inside you have both. That is not a set. I don't know. Yeah, I don't know how much mathematical training we have here, but that a set with two ones in it is that's not good. But closure solves this problem in a beautiful way. Long one and int one are equivalent, which is quite nice. And so we've got the same thing in hamif here. And it gets the closure answer. It has the same equivalence semantics as closure. Here's a set with just 1, 1 in it. That's quite great. But it's, it's basically as fast as the Java hash set. And so making the closure set takes a while, and making the hamif set is faster. There you go. There's your 15x again. Sweet.
Yeah, similar with that. I really like this example.
Okay, you want to talk through it?
Yeah, right. Just the same with map. Is that right?
Right. Yeah. I think that's right. And this one really you will run into in real life. You will get two data sets, and one of them will have integers in it, and one of them will have longs in it, and you will put them into a map, and you will be deeply confused. And so we grabbed just as much of the closure goodness as we could, because this is what speeds us up. Like the success of our business depends on developing software quickly. Running into the map has some longs and some ints into it is like not good. And so, so just sort of trying to suffer less from that stuff while, performing as close to the Java stuff as we can.
Yeah. So that was a little bit of ham-fisted. Could you summarize in 2 sentences what ham-fisted is?
Yeah. So it's a collection of data structures that you can use to implement high performance programs on the JVM with the convenience of Clojure data structures. Like one of the deepest insights that Rich had was that the combination of immutability and persistence puts you in a completely different realm of software development. The things that I worried about as a kid developing Windows software in C++, I just don't worry about at all anymore. And when you look at the history of Clojure, you go back into like what was going on in 2010, people were like, this is cool, but it's slow. And in some ways they were right, and in some ways they weren't trying very hard. And this just answers those questions. You can have the cake of Clojure's immutable persistent data structures and eat it too, and get your answers fast and make your customers happy. More than 2 sentences.
Yeah, thanks so much. We have 13 minutes now. I think we will leave a few more minutes for the bigger picture and where, things we wish to be seeing in the next year and so. So in a moment, we'll expand again, but maybe let us just keep going a little bit and have a little taste of dtype-next, if it makes sense.
Yeah. And so, as mentioned earlier, dtype-next is a library that's now built on top of Ham-Fisted. So you have some idea of what's at the bottom here. This collects up a set of interfaces essentially around random access data structures, mostly one-dimensional, but there is also tensors in there where you can treat a big one-dimensional random access data structure as higher dimensional, which we'll see in this very first example here. I don't know if you've ever tried, but in Java or in Clojure, you can use these AWT libraries to load images, and that's very convenient. But just getting the numbers out of them is no joke. And part of this was all heavily developed when we were doing a lot of convolutional neural nets, image recognition. We were processing images. We were synthesizing training data sets by noising up images. We were doing all kinds of things. And we wanted to use Clojure to get at the numbers inside of an image and work with them efficiently. And this is ultimately what that's about. When you load the image it is an AWT thing. Great. Yeah, so that's just some Java library thing. Picture of Chris's wife. That's lovely. But right away, DT here is the main data type API, and you can get the shape. And this actually makes sense. This is like how many rows and columns in my image and how many channels? 3. This is quite good. That information is probably relatively easy to get out of the Java interface. But on the very next line here, we turn it into a tensor, which is, in this case, a 3-dimensional view of a big one-dimensional list of numbers that represent the image. And you've got, 288 rows, 512 columns, and then 3 channels in each pixel. And then, it's nice printed, the pixels here. Those are the RGB values of the pixel. And then again, we're influenced by Clojure here. The tensor itself is a function of 2 arguments in this case, which is going into a certain row and column and pulling out a pixel.
Pixel
that is
3 values, right? A pixel, which is still 3 color components.
True, So that is the pixel, 3 channels. Thinking about the Java program that does that is already like, okay, I want to work with this thing instead. And this is how does this connect ham-fisted up to TMD? The data from the image is stored in a ham-fisted structure by the time we've ensured it as a tensor. That's close enough to true. And that is this random access one-dimensional array at the bottom. And a dataset column is a random access one-dimensional array. And so you're seeing the kind of, they're reaching for each other here.
In a moment, we'll see a dataset column. And
Great.
yeah, but maybe let us make the point that ham-fisted has data transformations that respect this idea of lazy and non-caching, right? And dtype-next has data transformation that respect this idea of lazy and non-caching. Ham-fisted, if I understand correctly, is very much about sequential data structures, and dtype-next is about array-like data structures, which means we have random access. We can access by index, right? So here, let us maybe give a tiny example of that before we continue. So we have this functional namespace of functional transformations. So we could take our tensor data structure. This is tensor data structure, right? And one thing we could do is ask for, a certain row, like a certain pixel of that data structure, like pixel number 4, 5, whatever, right? That's a pixel. But we could also first transform T by some functional transformation. Maybe let us amplify this by some number. So we could do something like that, right? So what we have here is that, we multiply these numbers by a lot. But what did we just do? Did we compute that for all pixels? No, only for the one we were asking for. So we were making only 3 multiplications because it is lazy. It is lazy and random access. It is lazy and we can ask for an element by index or a chunk of it by index, right? And it is non-caching, which means it didn't remember it anywhere. It didn't consume any new memory by this computation. If I ask again, it computes again. This way we can create those pipelines of many operations that don't require any intermediate memory storage, right? And
yes. And it's, were you going to say more?
No, just that it is a trade-off. Sometimes we do like to remember things, and we can with a Java array or something similar, right? So we are in control of these details now.
Yeah, and it's very interesting to think about what the type of the first element of that list is. Like when, DFN.
It is a function basically. Or it is something.
This is great. I think what Daniel said, just to reiterate it one more time, is exactly right. The ham-fisted is at the bottom there. It's our best ideas about storing data on the JVM in different types. On the screen, there's a uint8 type right there. This image is converted to a very convenient type that it's not Java native, and the dtype layer on top of that is giving this kind of random access view or lens on that underlying data. But in this, as you can see, in this capital F functional way, like the product of a tensor and 1000 is the type of thing that you can apply as a function to dimensions of the tensor and get back lazily computed values. This is,
Or slices. Yeah.
Whoa.
Yeah. I think it happened a few days ago that I had a chat with Lorelei, who is here with us and is going to give a talk about EEG, brain data, and so on. And we were trying to make sense of these tensors because Lorelei is using these tensors and data transformations to wrap basically Java objects which are Java representations of MATLAB files, right? And Lorelei explained to me that this is just a function. I was trying to find the words to say what that is, and Lorelei said, it is just a function, right?
Yeah.
That's what it is. You know, this lazy non-caching means it's just a function, but a clever one, right? Yeah. Great. We will have to stop in a moment, and so maybe we should say a little more, and then we'll go to the big picture, and then Kiran, if that is okay, we'll just slightly over time before we go to the discussion. Is that good?
It should be good.
Yeah,
Right,
thanks.
Yeah, was there one more dtype example? Or?
Yeah, so there is now this example, which is already about TMD,
Oh, perfect.
right? Yeah. So, right, you created this data set. That's how the data set looks like, right? And then you have this functional namespace, and you can add 2 columns, right?
This I think, this sort of closes the loop on those connections. So DS is the kind of data set that we've been talking about all day, presumably. Now, on the line, applying the keyword A to the data set, as we said at the beginning of this, the DS is a map. Keywords applied to a map give you the column. The column that you got out there is one of these data type views on top of a HAMF thing that's actually storing the numbers. And the same functional namespace here is, it knows how to add 2 of those things. This is the kind of array programming that was probably already discussed earlier too. But again, the result here is just the same kind of thing as we put in. So I didn't put this in there, but you could throw it in, Daniel. You could associate that onto DS as C or X or something like that. Perfect. And the result here is, of course, another data set with another column, the sum of the first 2. This is the kind of things people want to do. And excuse me. But again, we've arrived by way of everything that we just discussed. This is all functional. So DS is unchanged. Well, if we reevaluate DS after having done that, it will have just 2 columns. And this is the fundamental difference between like when you build this kind of thing, this pandas-like thing, out of these structures, you end up somewhere different. We're doing functional programming, which is what we're super committed to doing. And the joke I like to tell here is, I mean, if you do the equivalent thing in pandas, you're mutating things. And I think, as Rich taught us, like, that's a catastrophe, because you're either going to use more memory by making a copy of it, trying to recover this behavior, or you're going to spend a lot of time doing the work more than once, or both. And so, the functional data science story here is sort of like built out of these, deep structures that we've been talking about. But that's why it works. And these are just our best ideas so far. We are going to talk about the future here. This is far from done, but it is working. And that's where we are.
That's great. Yeah, we are just around the end time of this talk. Maybe just briefly over time, we'll just come back to the big picture for a moment. And this diagram by Joyner, and think about where we wish to be going. So I might comment a little bit on that, but maybe Harold, you wish to say something about what you wish to see happening about all that. Of course, we were just spending time with the low levels, with the deep roots, but maybe you can comment about any path.
Oh, right now you'd like to hear my thoughts?
If you wish
Okay,
to say
yeah.
reading words, yeah.
I think what I'll say at this point is that I think this conference is perfectly timed. We have, I would say, in 2025, hit a new kind of high watermark for what can be done with the system that's suggested by the picture that's on the screen right now. We are doing that work at TechAscent. It's super fun. Our customers are happy. I have a very similar workflow, thanks to Daniel's help, where I'm grabbing data from all over the place. I'm loading it into ripples. I'm viewing it with tablecloth. Tableplot. I'm doing math. I'm doing modeling with XGBoost, which is on this picture. One thing that's not on this picture that we're also making heavy use of is DuckDB. We have a connector from tech.ml.dataset to DuckDB. When you have, painful amounts of CSV and you want to do SQL-y things, DuckDB is amazing, and we have this connector. We're at a very good point where this stuff is all highly usable. Our business is proof of it. And I'd really like just more users of it. I would like more people to know the joy that I wake up with, and I'm going to solve a problem in a functional way, and I'm not, nothing bad is going to happen to me during the day. That's my kind of broad overview of the future. I think if we zoom in, one idea for some near future development, if you have a data set that is mostly empty, maybe you have 1 trillion rows and only 1 million of them are filled out sort of sparsely. There we have ideas for how we could work with this. The data set system uses far less memory than vectors of closure maps, but also less than pandas and other systems. So we often can fit more in RAM. But there are certain shapes that still explode us. And so, maybe we'll work on some support for sparse structures and things like that. But the actual development that's going on is being driven by users. They will find bugs, and the bugs are good. And we fix the bugs. TechAscent is continuing its investment in these tools, and other companies are investing in these tools as well. I can pay Chris to fix some bugs, but other companies can pay Chris to fix some bugs too. And that's I think the medium term future for our open source libraries.
That's great. I'll try to comment in a minute or two about a few directions we're looking to see about this diagram, and then we will move to the questions, if that's okay. So one thing that is noticeable here is that fast math, which is a core part of this story, is kind of disconnected from the others. And what it means is a certain incompatibility of data types. And it means sometimes copying and conversion between different types. And we have been having a few sessions on that. And that's something we can hope to improve by, maybe our next conference in September will be a story of that. Another thing is on the highest levels of ergonomics, some of the connections, again, connections between fast math statistics, for example, and table processing could be much improved. And we have some experimental code. And in this conference, we are not sharing much experimental code. We're sharing more of the stable part. So we are hoping to make something stable and nice around the connection of these. And then another thing that a few people mentioned today, Paula and Sam here did mention, is interop and the wish to make interop more robust and actually more detailed. and to make a good closure story for those specialized libraries in languages like Python that we may need. And libpython CLJ is something we didn't get to discuss much, and maybe in the questions we'll discuss a little bit. But there is another promising direction, and that is stdlang, the standard transpiler, which is becoming compatible with libpython CLJ, but with other languages and other runtimes. This project by Chris, another Chris, is a way to generate other languages from Clojure, but also connect to other runtimes in a systematic way. And the promise is that sometimes we may wish to connect to another runtime, a Python runtime, in the same process as we do with libpython CLJ that we haven't spoken much about. But sometimes we may wish to connect to Python as a separate process. So it can fail and crash without bothering our JVM, and we can run hundreds of them without bothering our JVM stability. And that's something that can be made with a very compatible experience without much code change, thanks to the standard transpiler stdlang. So that's a topic for another thing that we'll discuss in the coming months and in the next conference, hopefully. Yeah, so these are a few little hopes for the near future. Thank you for being a little over time. And maybe, I guess we can conclude this part unless there is any other thing. Yeah, so thanks.
Yeah, thank you too, Daniel. Great work.
Thank you, Harold, and thank you, Daniel. Great examples to showcase the difference between the closed data structures and the ham-fisted data structures. So thank you. We are open for questions.
So I have a very high-level question, if I may. So the fact that the library is called tech.ml.dataset implies that there are other tech.ml libraries. Is that right?
That's a great question. Yeah,
Okay.
yeah. This is a bit of a historical accident. So the that library was born at our last company, the previous company, and that company's founding principle, it was founded by a different person who was ex-DeepMind, and his idea in particular was to solve every business problem in the world with a neural net. This was 10, 15 years ago, and so that was ambitious. The development of our sort of original pandas replacement paralleled, we were also developing our own neural net toolkit. This was sort of before PyTorch was as good as it is, and before TensorFlow is as good as it is. And we had a pure Clojure neural network toolkit, and a lot of the tensor functionality inside of dtype is sort of the successor to what was the matrix representation in the neural net toolkit. And it was part of a larger suite of ML libraries, because that company was also doing, what do I want to say, consulting work with solving business problems with neural nets. And so that was that whole company. When that disapparated, we obtained the code and the ability to roll forward with things. So some of the things are just sort of historical accidents of naming. Another thing to say here that's very positive is there was a library, and you could probably find it if you Googled hard enough, called tech.ml, where we were organizing some of this. A lot of that stuff can't really be open source because there needs to be some IP inside the company, but it was like an open source view of some of our ideas around how to do that stuff, superseded completely by Metamorph ML, which I think sort of approaches the problem in a broader and better way. So the naming is a little bit unfortunate, though I do like the acronym TMD. The tech.ml.dataset was sort of, the datasets were tech.ml, but tech.ml thankfully is withered and replaced by metamorph.ml. And we can't really solve that problem for everyone at this juncture. Though I'd love to see it, what Daniel was saying about libpython CLJ. I think a libpython CLJ PyTorch connector would be amazing, because to the extent that we succeeded in solving every business problem with a neural net, we did so because working with data enclosure is just so much better. And so being able to do that work that we know is better in Clojure, but then still leverage PyTorch, I think would be very neat. I imagine we'll see something like that someday, though TechAscent isn't actively working on it at the moment. Does that answer your question?
Yes, it does. That's
great.
Very well.
Great.
Thank you very much.
Thanks for asking. Yeah, very cool.
So just to add to what Harold said, so there's a talk on SciNoj YouTube channel, the old tech.ml. So you can maybe explore that just for history sake. But I'd seen that talk, and that is a great talk.
Great, thanks. I see Paula has hand up.
Yeah, sort of building on what you've just been talking about, especially going through the libpython CLJ, but just generally in the tech data type versions. And I haven't been able to figure out what's V2, V3, and the documentation jumps between them. But there's easy copy-free conversion between NumPy tensors and V3 tensors. I was wondering about TensorFlow tensors because they're immutable, and so that would seem to be really compatible with our view of the world. And like, is there support in there? Does it have to be copied to NumPy and then across? What's the
That's
TensorFlow is what I'm having to work in all the time at the moment, and I do miss Clojure as I'm doing this.
Yeah. Let me answer the first part about the V2, V3 bit, and then I'm gonna have a follow-up question for you there. There was a moment, I don't remember, I should know the date, but we could find it. There's a Rich talk where he's basically justifying the fact that they called spec.alpha. And he made some really strong points about backwards compatibility, which we all love, the way that we upgrade Clojure and nothing bad happens. And we were influenced by those ideas, but have some different thoughts about them. And there's philosophical and technical and all kinds of interesting things to discuss here. And briefly, we experimented with putting version numbers in the namespace to participate in this kind of never break anything philosophy. And that's where the sort of V3s popped up. The interesting thing is, in practice, it didn't help. But we must try things, and we must roll forward, and we must measure how they were. So we typed some V3s in some namespaces or not, and it's not at the, maybe in a world where there are many thousands of people working on TMD or something, it becomes important again. But for now, we'll probably just be on V3 in terms of those namespace names. Now, to talk about the TensorFlow, you're using those from Python? the TensorFlow tensors, and are they? I'll reveal a bit of my ignorance here. Are those? What's their relationship to NumPy arrays?
They're related, and you can transfer data in and out of them. NumPy tensors are mutable, but TensorFlow tensors are not. TensorFlow variables can be built from a tensor, and they can be mutated.
Nice.
Um,
Is
I mean,
that transfer from NumPy into a TensorFlow tensor a copy operation, or?
I believe it is, yeah.
Yeah, that's interesting.
I don't use NumPy at all, except when
Oh.
I'm trying to get something out.
Yeah.
But I'll leave everything in TensorFlow as long as I can.
Yeah.
And I will use variables wherever possible. I'm using tensors. And in fact, a lot of the framework as they've built it looks like it would be very re-implementable in Clojure.
Nice.
So they set up what do you call it? A tape, what they call a tape around a block of code, and then anything in that that executes within that context, it records, oh, there was an addition done here, there was a multiplication done here, etc., and it can figure out gradients as it's going. And that allows you to do your back propagation.
Perfect. Yeah.
And a lot of it actually looks very much like when you attach a watch to an atom. But the tensors, as they're applying them, everything's being done with these immutable tensors. And so the weight matrix is immutable, and they generate an entirely new weight matrix. It's also immutable. And that's, it seems so familiar.
Yeah, it's highly related to our interest here.
I think it annoys Python developers that all of this is immutable.
Yeah, they prefer things to be non-functional.
Yeah. And I'm really liking it, and it feels like I'm very close to Clojure, but not quite there. And I was wondering, like, with such a small apparent step, have you got any support in there yet? Because I mean, TensorFlow and PyTorch are both like the standards for working with neural networks at the moment.
Yeah. I would say that, not that I know of, but I don't know everything. I would also say that, and we can take this discussion offline and figure out what would be involved. It can't be too crazy to do what you have in mind, because the TensorFlow tensor cannot be anything other than a big one-dimensional array of doubles at the bottom. And that thing cannot be anywhere else than in RAM. And we have the machinery, libpython CLJ proves it, for doing pointery things to big blocks of doubles in RAM. And so
benefit
I would...
of the tensor is that, it's in RAM, but it can also act, I think, as a pointer into GPU memory.
Yeah. And so when we had tech.ml and we had the neural network toolkit, we had the predecessor to these sort of dtype-next arrays, and we had the CUDA machinery for moving them to GPU RAM and back. Again, the important thing there is that in CPU RAM, where the source of them before they go to the GPU is, or when they come back, it's sort of I mean, I don't know what it is, but I would be super shocked if it was anything other than like a big block of doubles that we could fill up, point at, reinterpret as a D-type tensor, and do that kind of stuff.
Yeah, maybe I'll stop you for a moment. I apologize. Maybe I remember that like an hour ago, there were quite a few questions by people, and we thought, oh, we should keep that for the session with Harold. And while we're still here, maybe it makes sense to return to a few of them. So I didn't want to stop you, and I think it felt like maybe you had a few more things before you conclude this part, but maybe in a few moments we can move to other questions. So I didn't want to stop you, Paula.
Quite all right. Paula, are you on Zoom? Oh, maybe we lost Paula. Oh, okay.
Yeah. So
We'll
Aaron,
find
I
a
had
way
a
to contact
question.
Paula and continue that conversation. Super interesting one.
I think she said her username was Quell earlier, right? If I'm not mistaken.
Oh, I've seen that name on GitHub. Okay, yeah, we'll find a way.
The talk
I like
was
that story.
fantastic, by the way.
Yeah, I'm more interested in PyTorch than TensorFlow right now, but I'm also not solving problems with neural nets right now. So, yeah, what were these earlier questions, or what other questions have people got?
I had a question earlier about, so I'm a user of libpython CLJ, and
Great.
I was having some like memory performance issues when I tried to do this was like a year ago, so I don't know if this has been fixed by the latest stuff, but
Unlikely.
I had been having some memory performance issues when I tried to do certain like operations in parallel through libpython CLJ. So like an example is like I was calling like sentence transformers, and it was like seemed like it was working mostly okay. But then when I ran like a closure pmap over grabbing sentence transformers through libpython CLJ, like I had some issues where like the memory exploded even running the pmap in relatively small batches. And so I was kind of wondering, like, is that a thing? Am I going crazy? Like, yeah.
There's many interesting possibilities there. I think pmap in particular, like we were talking about before, this is producing a caching lazy sequence, and it's doing something else too. It's producing a chunked caching lazy sequence. And this one people hit a lot. It runs out ahead of itself, and it will compute values that you didn't ask for, which is unexpected if you're coming from a kind of like Clojure 1.4 level, or so you're coming from somewhere where, oh, I thought this was lazy, it wasn't going to do anything until I called first. And there's the amount that it runs out of and ahead of itself is actually hard coded. You can go find it, and I think it's like 32 or 25 or some amount. And oh, welcome back, Paula. Okay, I thought we lost you. But
it's 32.
32, and 32 is enough for anyone, or maybe too much for everyone. But you may be seeing that it did a bunch more than you thought it did. You may also be seeing the fact that the Python interpreter is not reentrant. There's something called the global interpreter lock, which is somewhat handled by libpython CLJ. Could be handled better probably by, and definitely has been handled better over time. But the idea of firing off a lot of these things at once is it actually is sort of like, oh, I'm not even sure what the Python interpreter is going to do here. We have done things in parallel from Clojure with Python. I mean, this is one of the original things that brought me to Clojure, is I was able to do things in parallel without thinking very hard. Like in 2009, I was writing code for game consoles, and I was porting pthreads stuff back to Microsoft Thread stuff for Xbox 360, and I was doing hard threaded things, and it sucked. It was like very, very, very hard. And then in the afternoon, I would parallelize something in Clojure by putting P in front of map, and nothing bad happened to me. And I did what I wanted the second half of my career to look like. We have parallelized things with libpython CLJ, but it often involves forking multiple processes, either JVM processes or other Python, and letting the operating system sort it out. I don't know if that answers your question, but those are my thoughts.
So basically your main thought is to like avoid PMAP when interoping with Python, because Python does weird stuff with that interop anyway.
Yeah, I think that's right. I think if you think about how would I in Python create the situation of PMAP over the sentence transformer, it's yeah, maybe there's a way, but maybe there's not. And so we're putting the interpreter in a situation where it doesn't know where that it's sort of like not built for. And so, but of course, there's other ways to task out the machine, I guess is my thought.
Is there like a specific way that you're already doing that? Like, do you have like, I don't know, like maybe any like either like open source code or like code samples
Oh, that actually does that?
that are actually doing that, or is that not?
No, but we could probably work up an example like and in fact, the example would probably look different than what the actual old stuff we have is doing, because there's better things in more recent JVMs for managing processes and stuff like that. So I'd probably look at doing it with that. Though, yeah, the first idea would just be the close your Java shell sh, and then either boot up some other Java process or other Python process.
Yeah, and by the way, this is the area where the new standard transpiler is going to be useful at some point, where it is trying to standardize the practices around these problems. Sorry, I didn't want to stop you.
No, that's good. Say a few more words about that. I didn't understand that part of it.
Yeah, so what Chris, the other Chris, did in the standard transpiler project was first creating a way to generate code in other languages from Clojure, JavaScript, Lua, Python, and so on. Second, have different ways to connect to runtimes of those other languages from Clojure. So one way to connect to a runtime is libpython CLJ, which is in the same process in a way. But another way to connect to a Python runtime is run a Python server and communicate with that in a different process. Or another way is run a Python server over a certain Python scripted app like Blender, for example, right? So you could have many flavors of Python runtimes you can connect to, and Java runtimes, and Lua runtimes, and so on. So one step was transpiling, generating code. The other step was having different variations of runtimes in a standardized way. The third step is implementing a standard library on top of that. So in a way, you can do some Clojure-like practices, some functional programming over those other runtimes in a standardized way without having to switch mindset between runtimes. So that's the promise. And in a way, it makes the Clojure JVM REPL, the usual Clojure JVM REPL, as one central place, which is like an operating system where you can reach all those other ones, shell out to other things and so on, but without any change of mindset between them. That's the idea. And there is a long way to make it all feel familiar and well-known, but we will be working on that. And I'm so grateful that Chris is sharing that with us. So I think that's kind of related to what you're talking about.
Yeah, that sounds relevant. And I think it just going to hijack your question about Python here, but I think part of especially in the last year, it's become very clear that data science problems are often best addressed by software engineering, and having a repeatable process, having a process that's running somewhere that other parts of the business can connect to and get answers from. The kind of like software engineering poor notebook oriented view of data science is like really poorly serving like real business use cases that actually just need software development. And I think what Daniel's talking about and what Sam's hinting at, some of these tools, yeah, and Paula as well, like I don't want to build PyTorch in Clojure. I want to use PyTorch or TensorFlow or sentence transformer things. And I want to build software out of them. And I want it to be as reliable as my Clojure programs are. And that's sort of the direction that we're headed.
Okay, so we are at time, but yeah, Daniel, do we have some more minutes before the next session?
So it turned out that we had this big hole in the schedule. Maybe I'll share the screen to clarify the picture. And I don't even know how it happened with all the schedule changes. So yeah, in a way, we can think about what we may wish to do now, which is maybe an open chat. Maybe we stop recording and keep chatting and so on. And right, so that's the conference website, just moving things around. And we go to the schedule and you see this is Friday. And now we are around 6:30 UTC, and at 7 we'll have the last data analysis talk of today by Lorelei about brain data and EEG and all that. So we have like half an hour to chat for those who are able to stay, and yeah. I think Harold may need to go in a moment.
Yeah, I should run, but I would encourage this group, which seems like an amazing group. Everybody get on Zulip, and we can continue these conversations. I really like, when things pop up on Zulip, we start all the interesting conversations that lead to the development of all of this stuff. So super encourage everyone to get on Zulip. I'd love to chat about these questions or any other ones that come up. And I'm really looking forward to watching the recording of all of this in the future. So thanks, but I do need to run now.
Thanks so much, Harold.
So I had a question, Daniel, that from the previous session, and if Harold is around, he can still answer. So I love the idea that I can use ham-fisted collections to make Clojure faster, and and then there is a dtype-new. So how do you distinguish them? Like how do I do mental model when to use ham-fisted, when writing normal Clojure code, and when should I fall back to dtype-new?
Yeah. So yeah, maybe in a moment we could share the REPL if that's what we like to do, unless there are any other topics. But I haven't used much of ham-fisted, which is in a way the lowest level. Ham-fisted is offering versions of different Clojure-like data structures. I mean, Clojure data structures which are similar to the core Clojure, like map and sequence and set, which are efficient versions of them and efficient functions to process them. And a lot of that is still sequential in a way, which means going through a sequence element by element. And dtype-next is about array-like structures. So we have this idea of random access by index. Like I wish to have elements at position 1 million and not care about all the other elements. So I think that's the main distinction, the way I understand it. Even though, historically both things have been growing the way they emerged, but I think dtype-next is about random access, about being able to access by index. And ham-fisted is about the different flavors of data structures which are similar to the Clojure core. And both have this idea of lazy and non-caching, right? That we transform something, but we actually haven't even allocated any memory, but we have like the transformation as a view on top of the previous thing, if we like, for performance. And we can compose these transformations and so on. Yeah.
Right.
Yeah. But should we, I mean, we could just share the screen and try some things with ham-fisted. I haven't tried much, but we could try. Should we do that? Or are there any, what do you think, Kiran?
Yeah, we can try that. I also had one more question, or suggestion and feedback from you, is that one of the ways that I was thinking, like how do we get people to try tech.ml dataset or this few things is there a framework or library that can give SQL interface? Because a lot of people are very familiar with SQL, and that's becomes a gateway entry into trying new things, because you can still write like big SQL to do data analysis, and then slowly you start exploring the framework.
You mean actually writing SQL, like select and all these things, but to access closure data structures? Is that right?
The tech.ml dataset structure.
Yeah, specifically tech.ml dataset access through SQL. That's fascinating. Oh, wow. Should we do that? Should we try?
Yeah, we
Yeah.
can definitely try that, because from my experience, like I was a big data developer, I mostly did Spark, but recently I'm exploring Polars, and my entry into that was it had SQL interface. I did not have to relearn few things, but I ended up exploring the framework more because I could use it.
Yeah. Would it make sense to ask you, Kiran, to talk a little bit about your recent experiences with that, if you wish? I mean, because you have been doing some things
Sure.
this data analytics project that you shared, this open source project. Yeah.
Sure. So everybody knows Pandas. Pandas is very famous framework in Python world, which allows you to do data processing. So Polars is the newer kid on the block. So the URL is pola.rs. What it is actually is it's a re-implementation of all this, just like tech.ml dataset is in Clojure. Polars uses Rust, and that's what makes it really fast. So, in fact, on a single node machine, they claim to be the fastest. I would love to benchmark that with tech.ml dataset, but and they provide a Python interface. So you can, whatever, let's say you have a data analysis script written in Pandas, you can convert that into Polars and get all the, like it is not a drop-in replacement. There are new functions, etc. But what good thing they have done is they have provided SQL. So even if you don't learn any of the Polars functions, like how to process data, how to rename columns, how to process columns, uh, you can still use Polars through SQL interface. And one of the things that they have done is lazy frame, which is laziness, like we saw in earlier talk, that in lazy frame, it builds a transformation map. It doesn't apply anything to dataset. And when you say collect, it applies all those addition, multiplication, etc. to the dataset. So that's also something they have done, and they have done query planning around it, etc. But yeah, internally it is all written in Rust. You are on mute, Daniel, if you're speaking.
Oh, I'm so sorry. Yeah, I was just wondering. I know that Kiran, you have been creating this project on top of Polars recently. So should we talk about it, or should we talk about it another time?
Sure, if you have time, I can talk a little bit about it. What I'm doing is where you need data set is often like I'm working with a customer and they get from their tech, they are a kind of a executive level, they get a data dump every month from their tech team, and sometimes it has been like just insight, and then they have to work with a data analyst to get more depth, and sometimes there's a back and forth and it takes time basically, right? So the request that they had was that can I connect to can I download the data set, raw data set from Snowflake, and can I analyze it? So one of the ways that we did was built a MCP server. So there is a step that is not exported on server. There's a open source here. Is that the data is downloaded from Snowflake onto the local machine, and then Polars is used to build the MCP server. So the executive can ask questions to their data using Claude, and it pulls all the necessary data, like what was the how many orders were confirmed last month, and how many orders were fulfilled, what was the like fulfillment rate of it, etc. And they can even dig deeper and keep going deeper. So that enables them to do uh, like not be blocked on somebody else and use the latest technology. One of the thing that is it doesn't send like since the some of the times it was 100 million rows and sometimes 500 million rows. The worry was we can't send this data whole data set to LLM, but still we want to analyze it. So the Polars becomes the bridge between the large data set and helps analyze it.